This video looks at performance within predictive control. We have established already that using prediction and/or anticipation within control is logical, and we've also shown how you can form predictions using common discrete models, and that's the previous 5 or 6 videos in this series. Earlier on, what we said was the main components of a predictive control law were things like prediction, receding horizon, modelling, performance index, degrees of freedom, constraint handling, and multivariable. Well, we've done prediction and we've implicitly done modelling in the earlier videos. So what we want to look at next is this concept of a performance index. What is it? How do we define it? How do we use it? Now, when you're undertaking control design, the designer must have in their minds some requirements which they can use to compare alternative strategies. Otherwise, how do we know whether control law 1 is better than control law 2, or vice versa? Now, the normal answer is, well, if it meets the requirements better, then it must be a better controller. But what are your requirements? Now, we've got an example here for you to look at. Which of these plots are best? So, for example, if I start with G4, you can see G4 is the smoothest, but it's relatively slow, okay, and it's got a very slow rise time. So if your criteria was I want a very smooth response with no overshoot, you might go for G4. What, however, if you wanted something to be very fast? Well, you might go with this green plot, because if you look at the green plot, you'll see it's got the fastest rise time. And indeed, even the settling time isn't too bad. If you look, it settles reasonably well, much faster than G4. So okay, it oscillates, but if you're not bothered about oscillation, you're bothered about getting to the target quickly and then settling fairly quickly, the green might do the job for you. What about the red one, G1? Well, the red one's got a slightly smaller overshoot than the green one, but it's slightly slower. So you've got a decision here. You might say, well, it's got a smaller overshoot and that's quite an important criteria, so I prefer the red one to the green one, and I accept that it's a little bit slower. What about the blue one? Well, the blue one's got an even smaller overshoot than the green and the red, but it's much slower again. So is that better than the red and better than the green? Well, you decide. But of course the interesting thing is the blue one is also slower than G4. But you could argue it's better than G4 because its rise time is much faster. Now, where does this all lead us? What you'll see we're getting at is you cannot just arbitrarily say G1's better than G2 or G4's better than G3. It's not obvious which response is best and why it's best. So humans often use rather vague performance indices when making choices, and we trade off between different aspects such as rise time, overshoot and settling time, and here's the key thing, in somewhat arbitrary ways. Predictive control is different because it's based on a precise numerical optimum, so there's no ambiguity. Of course, in order for this to work, we need a precise definition of optimum performance. And herein lies a problem. This definition of optimum is actually arbitrary. And that might sound a bit perverse to you, but in practice that's the case. You need a precise numerical definition in order for it to work, but that definition can be arbitrary. And what you need to remember is this definition is a tool that is used to enable a unique solution. It simply makes life easier. So what are the different indices that you might choose to use? You might say, right, I'm going to define best as the one which has the fastest settling time. Or I'm going to use it as the one that has the smallest actuation energy in order to avoid fatigue and minimize fuel costs. Or I might say the one that has the smallest error on average. Or the one that has the fastest rise time so that I get close to the target as quickly as possible. or the one that minimizes the maximum deviation when I have a disturbance hitting the system, because that ensures that my quality remains within a given tolerance, and so on. Now, you'll see there's a large number of possible performance indices you can use, and using the word arbitrary is perhaps a bit cruel because it depends on the context, but what you can see is the choice you come up with may not be neatly linked to anything in practice. And the problem with many of these criteria, and this is really key, is they're actually non-linear in any of the parameters that we can use, and therefore they do not lead to tractable optimizations. So the sort of performance indices that you might like to use are not easy to use, and that's a problem. If you look at your conventional feedback loop, and here's a simple one with an input disturbance model, and I look at the mappings from the target to the input-output and error, or the disturbance to the input-output and error, and what you notice is they're all non-linear in the parameters M of the control law. So let's look at these in turn, and you'll see I'm summarizing the problem, which is that the criteria you might use, many of them are non-linear in the parameters that you can choose, and therefore they do not lead to tractable optimizations. So what's the link between settling time and the parameters of a control law? And you find in general you will not find an analytic expression. What's the link between actuation energy and the parameters of the control law? And again, you'll find it's difficult to get an analytic expression. What about the smallest error? Something like the modulus. If you say by smallest error, I mean the integral of the modulus. And again, you'll find the relationship between that and the controller parameters is not usually linear. So we've got a problem. If you come up with some performance criteria, and here obviously this one's just made up, and I said to you, choose X to minimize this function, you might say, yuck, that's going to be a bit of a problem, it's non-linear, etc., etc. Yes, I can do it, but it could be difficult, it could be ill-conditioned, etc., etc. Alright, so we don't want things which are highly non-linear because they're difficult to operate with. But what about continuity? If I said to you, where's the minimum of the function that I've plotted down here? Well, hopefully you can all see that the minimum is actually down here. However, this function, if I write it, is discontinuous in the derivatives. So if I said to you how easily could you identify that minimum, then you'd have a bit more of a headache, and you might find that your optimization is equally likely to come up with a point like this, which has a continuous derivative. So we have problems. Sorry, I expected a box there. We have problems. We don't want horrible expressions like that. We want continuity. So what are we going to do? Simple measures of performance. We want things which have continuous derivatives because they allow us to have robust and simple optimizers which converge in a good time period. We want functions which have a unique minimum, because if there are lots and lots of different minima, how are you going to find the global minima? Well, it's not straightforward to guarantee unless you have some sort of bounding box. We want functions which do not contain nonlinearities, because again, nonlinearities are hard to deal with. If I have something like modulus of A, then in order to do the optimization, I need to know, is A positive or is A negative? And that is difficult to handle. I want functions which are always positive, because a negative cost is meaningless and could be misleading. So where does this lead to us? If you look at polynomials and exponentials, you'll find they broadly meet the four criteria that I've put above. They have continuous derivatives. If they have minimum, they're unique, they're not non-linear. They can be always positive, we'll get to that in a minute. Things like sinusoids do not have a unique minimum, so we don't really want to deal with sinusoids because we have a lot of minimum then. Exponentials actually have no stationary points, so we might want to exclude them. If you look at polynomials like a straight line, f equals ax plus b, then what you'll find is f can go to minus infinity, and therefore it's not a particularly useful function to have in an optimization. If it can go minus infinity to plus infinity, where are you going to get your stationary point? If you look at polynomials like cubics, they can have more than one stationary point. Certainly higher order polynomials have multiple stationary points, so that can be difficult to handle. And so where we end up with is the functions that are easy to use is just quadratics. And you might say, golly, that's a bit restrictive. However, when you're working in industry, what you find is there is a criteria that says simpler the better on average. And you'll find if you use other functions, you tend to find optimizations which are not as simple. And you only want to use the less simple if you have to, if there's a real benefit to it. So what we end up with is performance based on quadratics leads to sensible engineering and simple optimizations. So there's a typical quadratic, and what do you notice? Lots of good things. In engineering, energy terms often linked to the square of a state, and a quadratic has a square in it. Could be an x squared or an x minus alpha squared, so it makes good engineering sense to weight things like x squared terms. X squared terms are always positive for any x, so as long as you set up your performance index to look something like this, x minus alpha squared plus beta, you can ensure that your performance index is positive for all x, which again makes good engineering sense. You'll also notice that quadratics penalize larger deviations heavily, but not small ones. So for example, if you're within the region of the optimum, here I've marked it as 1, then sometimes you don't care if you deviate a little bit around 1. It doesn't make that much difference to your engineering costs. And you'll see the quadratic doesn't particularly penalize small deviations about the optimum. But what it does do is it penalizes heavily larger deviations. And again, you might argue that makes good sense. And of course, the other thing is it has a unique minimum, which is nice when it comes to optimizations. So, what do we get? Critically, right, if I scrub those out so we can see, the optimum changes smoothly and slowly with small changes in parameters, and so you don't get erratic behavior. And so quadratics tend to work well. In summary, therefore, the use of quadratic performance indices is the most common choice within the literature because they result in smooth and robust control designs and well-conditioned optimizations. Earlier work did look at using one norms and infinity norms and other things, and while that might make some sense if you're doing parametric approaches or the robust case, in general, the tuning you got was a lot more erratic, not nearly so smooth, and so you'll find there wasn't much focus on this area because people didn't find the performance particularly promising. Now interestingly, at the bottom, what you'll be seeing perhaps is this means that the performance indices that are popular in predictive control tend to be quadratic, and that says that there's a very strong link with LQR strategies, and that's something we will revisit in later videos.